Very good morning, one and all. Today we are going to discuss a very important topic about the counters. So the counters, you know very well. So counters can be of two types. One is a up counter as well as down counter. This can be categorized as both synchronous as well as asynchronous counter. So today we are going to design a circuit with this. You know very well the counter may be of up counter or down counter. Either that may be 0 0 0. If it is a 3 bit, it will be 0 0 0. Then if it is an up counter, so I will write here. So 0 0 0. If it is up counter, it will be moved to 0 0 1. If it is still it is an up counter 0 1 0. So 0 1 1. It goes like this. So up to all ones. And if it's still up counter, then that will be of 0 0. It will be get reset state. If it's a down counter, there will be of reverse process. So initially it will be of all ones, then it will be get decreased by 1. So by thing at last it will reaches all zeros. So this was the thing for down counter, right? Suppose in case of question may be asked to design a counter, will have a sequence of, will have to generate the sequence with 0 1 3 7 6 4 0, that is some random manner. So how we are going to design this counter? Okay, so today we are going to see that only, how we are going to design the random number sequence counters, right? Okay, so now the question is, so design, I'll write the question also. Design a counter with the sequence, the sequence will be of 0 1 3 7 6 4. After that it has to be comes to the initial state, that is 0. So this part has to be repeated, right? So for this, the first we have to analyze the number of flip-flops required, right? So he, since for the given sequence the maximum value is of 7, so the maximum number of flip-flops required is maximum is 3. So the maximum number of flip-flops required is equal to 3, because you can able to generate with the help of 3 flip-flops 0 0 0 to all ones, that is 0 to 7. So in our given sequence 7 is the maximum value, we can able to work with 3 flip-flops, right? So here it was not given what type of flip-flops that we are going to use for design, right? Let it be of we can consider any type of flip-flop. We'll consider here, it will be of JK flip-flops to be used for design purpose, right? So we have first, the first step we have to analyze the number of flip-flops required based on the sequence given, and then we have to analyze what type of flip-flops has to be used. So in some problem it will be given, so design a counter with the sequence, then sequence will be given with the number of flip-flop, I mean with the type of flip-flops may be specified. So in our question the no flip-flops are specified, so we can choose JK flip-flop. Okay, so in order to design with the help of JK flip-flop, it is essential to get the excitation table. So without this excitation table you cannot derive this and you cannot design this counter. So excitation table, you know very well, it's help to find the inputs, right? So you know very well, there is a q of n is a present state, q of n plus 1 is next state, then we have two inputs j and k. Qn is 0 0. If it is 0 1, then it is 1 0. For 1 1, if both are 0 0, then j is 0, k will be of x. If 0 1, then j will be 1, 1 will, k will be of x. If it is 1 0, then j will be of don't care, k will be of 1. And if both the present state as the next state is high, that is 1 1, then j is a don't care, k is a 0. So without this excitation table you cannot solve this. This we already discussed in class, right? This excitation table, how we are analyzing or how we got this excitation table. Now comes to the table. So the present state I'm going to write. So here present state is first, present state, then we have next state, then we have, so we analyzed 3 flip-flops are required. So I'm writing JAKA, JBKB, and then JCKC. Okay, so present state, so present state, then next state. From this we are going to analyze what was input for all 3 flip-flops. Right. So let us, I'm considering 3 flip-flops will be of A, B, C. Let it be of A, B as well as C. So usually we are representing next state as A plus, B plus, and then C plus. Okay, so this was our JAKA, JBKB, JCKC. Right. Right. As for the given sequence, the first sequence is 0, 0, 0. Okay, as for the given sequence, the first sequence is all zeros, right? I mean zeros, the value is 0, and the next value is 1. So the present state is 0, 0, 1 now. Then the value is 3. The corresponding binary value is 0, 1, 1. Or if you, this is the one type, you can write for other type also, that I will tell later. So 0, 1, 3, then 7. The corresponding binary value is all ones. Then 6. 6 corresponding value is 1, 1, 0. Let's complete the table. The last value is 4. For 4, it is 1, 0, 0. Right? Let's complete the table. Okay. Right. Now we are going to write how or the next state for the given sequence. So you can see here, I will write in some other color. Right. So the first thing given was, I mean the first sequence is given as 0. Okay. First one is given as 0. So then the next state is 1. Then the next state is 3. Then the next state is 7. Then the next state is 6. Then the next state is 4. And then this gets repeated. Right. So this gets repeated. So again 1, 3, 7, 6, 4, 0. So if 0 is the present state, right? So look at here. If 0 is the present state, then the next state is actually 1. Right. So we have to write for 0, 0, 0. The next state is 1, 0, 0, 1. If 1 is the present state, look at here. If 1 is the present state, then the next state is 3. So 0, 1, 1. If 3 is the present state, then 7 is the next state. If 7 is the present state, then 6 is the next state. 1, 1, 0. If 6 is the next state, then 4 is the next state. If 4 is the next state, then the cycle gets repeated. So it will comes to 0, 0, 0. Right. Hope you will understand. First I'm writing the present state. I will repeat. First I'm writing the present state for the given sequence. So here I'm writing the decimal value 0, 1, 3, 7, 6, 4. Then I'm writing all the present state corresponding binary value for the given sequence. Then the next state is computed. So if 0 is my present state, then 1 will be the next state. If 1 is my present state, 3 will be the next state. So like that, I wrote present state as well as next state. Now comes to the excitation table. So here, now we are going to compare. In order to get the output of J and K, we have to compare this A with A plus. right? That is qn with qn plus 1. That is, this is present state. So this is present state, this is next state. So from this we are going to analyze the inputs. Okay, so now we are going to compare the 0 with this 0. If both are 0, so j is 0, k is don't care. Okay, next again 0 0. So we'll have from the excitation table 0x. Next 0 1. 0 1 means 1 x. So both are 1 x 0. Again both are 1 x 0. Next 1 0 x 1. So these things I am obtaining from the excitation table. Okay, so I can write it for JBKB as well as JCKC. Now I have to use another color. Now I'm going to compare this this 0 with this 0. Okay, so 0 0 again 0 don't care. Next 0 1 1 don't care. Next 1 1 don't care 0. Then 1 1 don't care 0. 1 0 don't care 1. Next 0 0 0 don't care. Right, similarly I can write for JC as well as KC. Now for this I am going to check this with this, that is C with C plus. That is the present state is C, next state is C plus. I'm going to compare present state C with C plus. 0 1. 0 1 means 1 x. Please don't care. 1 1 don't care 0. 1 1 again don't care 0. 1 0 don't care 1. 0 0 0 don't care 0 0 0 don't care. So keep in mind. So in order to obtain this JAKA, I am going to first compare this with A with A plus. That is my present state with next state. Okay. Okay. After analyzing this inputs, that is J flip flop, JK flip flop, JBKB flip flop, JCK, there is 3 flip flops. After analyzing these inputs, now we are going to do the K map for the given expression, right? First, we are going to solve for JA. Since it is a 3-bit variable K map, A BC 0 0 0 1 1 0 1 1. This is for 0, this is for 1. Okay. Okay. Now I'm writing. So for all zeros, J. I'm looking for now this J alone, right? So by writing this 0 0 1 don't care don't care don't care and then don't care. Okay, right. So after this I'm now simplifying this K map. I'm going to group all these 4 variables, right? For this you know very well. So how to do the K map? J is equal to variable is B. Now the input for J is actually B, right? Next, similarly you can do for KA, JB, KB, JC as well as KC. After analyzing this K map, we'll get KA is equal to B bar, JB is equal to C, KB is equal to C bar, JC is equal to A bar, Case is equal to A, right? Now we are going to implement with the help of three JK flip-flops. Based on this obtained expression, we are going to design the counter now. I'm drawing for three flip-flops, right? So first flip-flop, second. If this is using came up. If you don't remember, you can write using came up. Okay, this thick the flip-flops. So I'll write J K A J B K B J C K C. Right, these are the flip-flops. So this is A flip-flops. This is B flip-flop. This is C flip-flop. Right. So I'm considering this is a synchronous thing. Hence, I'm giving clock pulse common to all the flip-flops. So clock pulse applying. Right. So this is actually a clock. Okay. Now we had given the clock pulse. So the output will be of this is actually A, that is QA or A, whatever you want you can use. This is A bar. So if this is QA, this is definitely a complement of this output, right? This is a B, this is B bar. So we use the notation as ABC, hence I'm using the same ABC here for your easy understanding. This is C, then this will be of C bar, right? What was given, what we found, J is equal to B. So A, B. So the output for the input to the first flip-flop J is actually a B, right? So B is the output. Then for KA, it is B bar. Hence I'm going to connect this B bar as a second input to the first flip-flop KE. So as per the K-map expression, K is equal to B bar. Hence I'm connecting K is equal to B bar. Got it? Then then come for JB as well as KB. JB is equal to C. So JB, I'm going to connect the output of third flip-flop as B of C. Right, then KB is equal to C bar. So KB, another input is C bar. Right, then JC is equal to A bar, KC is equal to A. So JC is equal to JC is equal to A bar, KC is equal to A. So KC is equal to A, hence I'm connecting A to the KC. Right, similarly for JC is equal to A bar. So I'm going to get A bar that was connected to the JC. So JC is actually an A bar. Right, that's all about the design. So this is actually an MSB bit. This is an LSB C. That's all about the that's all about the counter design for the given sequence 0 1 3 7 6 4 0. Right, so I'll repeat the procedure. First of all, you know very well the counter. Don't think here it was not given as an up counter or down counter. Here some sequence was specified. So 0 1 3 7 6 4. After 4 the same sequence gets repeated. right? Okay. So for that, for the first step, we are going to analyze how many number of flip-flops are required. So for that, the given maximum value is 7. Hence, so in order to represent this 7 band representation, triple one. So 111. So for that, we can able to use maximum 3 flip-flops. So hence, I'm using 3 flip-flops here. So maximum flops record is 3. That is, it can be varied from 000 to all ones. Next step, we are going to analyze what type of flip-flops that we are going to use for design. Here it was nothing was specified, hence I am choosing JK Flipflop. If you want, you can use D Flipflop or T Flipflop, whatever maybe you can use. Right. So after analyzing this flip-flop, we have to write the excitation table for the decided flip-flop. Right. So the excitation table helps to find the inputs based on the present state as well as next state. Okay. So the present state is Q1, let it be of Q1, next state will be of Q1 plus 1. So 0, the possible 2-bit combination is 000110 as well as 11. For that, the corresponding input is JK. After arranging this excitation table, you can form the state table here. Okay. The present state, next state, and then these are the inputs, right? So the present state is I'm considering A, B, C, and next state as A plus B plus C plus instead of Q Q1, Q. Or you can write here QA. This will be of QA plus bar. Sorry, QA plus. This is QB, QB plus, QC, QC plus. Whatever you want, you can write. So after writing this present state, I'm writing in the given sequence order. So 0, 1, 3, 7, 6, 4 was given. The corresponding binary value was written in the present state. If 0 is the present state, then the next state is actually 1. If 1 is the present state, 3 will be the next state. If 3 is the present state, 7 will be the next state. So accordingly, I wrote the next state values. The next step we have to, with the help of this excitation table, we have to find the inputs of the flip-flops JK, JB, as well as JC and KC. For that, I am comparing A with A plus. I can get J. B with B plus. I can get JB, KB. Right. So for that, after completing this table, next we are going to analyze the K-map. Using K-map, first we have to find for JA, then for KA, JB, KB, JC and KC. So after, with the help of this K-map, after obtaining the expression JA, KA, JB, KB and JC, KC, you simply want to draw the flip-flop first. Then since it is a synchronous one, hence the clock pulse applied is common to all the flip-flops simultaneously. After this, just I'm connecting the output of the first flip-flop is A and the complement is A bar. Similarly for second as well as third one. So B, B bar, C and C bar. So we obtain the expression, just I connected all these things. Okay, that's all about the design. This is one of the important question in end semester point of view. Okay. If you have any queries, just ask me. Thank you.